So this lecture is going to be about oxidation states and how to assign oxidation numbers. Most of this you're just going to have to memorize. So when we're talking about oxidation states, we're really talking about not being an ionic charge like we have in the past, where something breaks apart and gains a permanent positive or negative charge, such as in ionic compounds where you have the sodium and the chlorine dissociate and break apart, where sodium will get a +1 charge and the chloride ion will have a -1 charge. We're really talking about imaginary charges. They're not calculable. It's just simply based on a set of rules. And this allows us to determine how electrons are gained and lost when there's not specific ionic compounds involved. So there's a couple of rules, and the rules have some priorities. You're going to see that many of the oxidation states are very similar to those elements' charges, but again, these are not actual charges. So free elements, or elements that are in their free state or in their natural state, have an oxidation number equal to 0. So for example, if we have just solid sodium, it's going to equal 0. If we have a diatom, such as chlorine gas or nitrogen gas or oxygen gas, you know, those Cl2s, N2s, O2s, etc., those are in their free state, so they have a oxidation state of 0. Now, if we have a monoatomic ion, meaning we do have a charged sodium, for example, not a solid sodium in its free state, the monoatomic ions have an oxidation state or number equal to their charge. So sodium as an ion is +1, so its oxidation number is +1. And if we look at this ionic compound here, the sodium chloride, we are looking at sodium. This would be a +1 charge. The chlorine would be a chloride ion, giving it a -1 charge. So these would have an oxidation number of +1 and -1. The sum of all the oxidation state numbers must equal the overall charge on the compound. So if the charge is neutral, meaning has no charge, then the oxidation states must equal 0. So then we have oxidation states of polyatomic ions, and everything within the polyatomic must equal the overall charge on the compound. So we know that oxygen, the oxygen always and forever will be -2. That never changes. Couple of rules are the most electronegative element gets first dibs on the negative oxidation number. So even though nitrogen would have a charge of -3, it is less electronegative than oxygen. So nitrogen in this case gets the positive oxidation number. Again, oxygen is always 2-. So the whole charge on this nitrate polyatomic is -1. Therefore, oxygen is a -2. There are 3 of them. We know that from the chemical formula. And they must equal and add up to -1. So the only choice is that nitrogen is +5. Okay, so I'm just going to write that a little bit of a different way here. So if we were to say we know oxygen in this nitrate, we know oxygen is always 2-, and there are 3 of them. We have no idea what N is, but we know they all must equal -1. So if we just make this a simple algebraic equation, we're going to have x minus 6 equals -1. So then in this case, nitrogen must be +5. Okay. Group 1 metals have an oxidation state equal to their charge, which is +1. Group 2 metals have an oxidation state equal to their charge, which is +2. The transitional metals we would have to figure out, and the nonmetals we would have to figure out based on what they are bonded to. Okay, so if I had, for example, NO, we know that oxygen is always 2-. That means this whole thing overall is neutral because I haven't written a charge. And it must be, in this case, that nitrogen would take on the positive charge, the positive oxidation number, because it is the least electronegative of the two. So it must be that nitrogen in this case is +2. Okay, so the nonmetals, you just got to kind of see what you have and what you're working with to mathematically figure it out. All right, this chart right here is a good chart to memorize. Fluorine, all the halogens, the group 17, they're all going to have a -1. Hydrogen is usually +1, but there are times that it can be -1. Okay, again, it's just going to depend on what it's in, what it's bonded to. And then finally, in their compounds, non-metals have an oxidation state according to the table on the right. All right. So again, the rule is most electronegative gets first dibs for the negative oxidation state number if we only have nonmetals involved. And we're going to treat many of them with an oxidation state number that is very similar to its charge. However, oxidation numbers are not a charge. If we look at some examples here, the first one, chloride gas here, Cl2, it's in its free state. We know that because it's in its diatomic form. Therefore, the whole thing overall has a oxidation state of 0, and each chlorine ion has chlorine atom has an oxidation number of 0. It's in its free form. We know that because it's a diatom. We recognize it as that Cl2. So remember, O2, N2, Cl2, F2, I2, etc. The 7 diatoms. Oh, and don't forget hydrogen. So those are in their free states. This is very different, you will note, than the chlorine involved in NaCl. This chlorine is not the same as this Cl2 right here. They are different. Okay, the next one, sodium ion, is going to have an oxidation state of +1 because Na is a group 1 metal. Therefore, it'll take on the oxidation number of its charge. And its charge is +1 because it's a group 1 metal. Therefore, its oxidation number is +1. Kf, we have to look at both the K and the F. Here we have an ionic compound. The potassium will take on an oxidation number equal to its charge, as will the fluorine ion. So they must net out to 0. So you can see here, if fluorine is going to be -1 and potassium is going to be +1, they must equal 0. CO2, same way, it all applies. So we have oxygen, which is always 2-, and there are 2 of them. Oxidation state of oxygen is always 2-. There are 2 of them. We know that right from the chemical formula of CO2. The oxidation state of carbon, we have to figure out, but we do know that all of them must equal 0. So if we know we have x minus 4 equals 0, the only choice for the oxidation state for carbon is +4. Carbon is less electronegative than oxygen, therefore it takes on the positive oxidation number. O and oxygen is always -2. The next one is SO4 2-. The oxidation state for oxygen, again, 2-. The whole thing, all the oxidation numbers added together must equal -2 because there's an overall charge on SO4, and therefore there's an overall oxidation state of -2 on the entire polyatomic. So oxygen is always 2-. There are 4 of them. They must add up and equal -2. So if it is x minus 8 equals -2, the only choice for sulfur is that it is going to be +6. And then finally, K2O2, same rules apply. Oxygen is -1. The potassium is +1. we know that they must be equal. So in this case, there's a shift in oxidation number. This is one of the exceptions to the rules. You have to, again, just be able to figure this out. In this case, because it is ionic, the positively charged potassium in the ionic compound gets priority for oxidation number, meaning potassium is +1 in and of its own right. And there are two of them. Potassium has a charge of +1, therefore an oxidation number of +1. So it must be that in this particular special case, oxygen is now 2-. You can practice these that are listed below. You can pause and write them down and try to practice them. If you need the answer key for that, let me know and I can provide that for you. But do go ahead and practice these. We are going to use these oxidation numbers in the next lecture to be able to see what's happening with the movement of electrons. We're going to study this by way of studying redox reactions. Redox reactions just mean that electron movement must occur for a reaction to occur. You will note that when we had ionic compounds involved in a reaction, that we said, well, in order for to say a reaction occurred, a precipitate or a solid must have been formed. You will notice here there are no solids being formed, but a chemical reaction is actually in fact occurring. It's occurring because electrons are moving from one thing to another. So if we just look at the magnesium, for example, the magnesium is in its free state. We know it's in its free state for two reasons. The first reason is there's no charge assigned to it. And the second reason is it is not involved in a bond in any way, shape, or form. There's nothing it's bonded to. It is just simply solid magnesium, and it's how it would occur in real life, naturally in nature. So it's in its free state, giving it an oxidation number of 0. But in the product side, what we see is that it changes from 0 to 2+. Okay? So when we look at oxygen and hydrogen, in this case, there are different things happening with the oxygens and the hydrogens, and we're going to look at each individual ones of those in just a minute. But in this case, it's a +2 charge here. In this case, it's free state, so it goes from 0 to +2. That's a loss of 2 electrons. If we look at just the hydrogen, hydrogen is always +1 when it's involved in an all nonmetal compound. So it goes from +1 here to +1 here. That means there's no change, so we can ignore it. Then finally, if we look at the oxygen, we're going to see it's a -2 because that's the rule, and it's a -2, so there's no change. So the question is, how do we figure out what is actually changing? If we already had a loss of electrons, where do we have the gain of electrons? If there was a loss of electrons from one thing, those electrons must have been gained by something else. That's when we have to look at the other product, the hydrogen gas. If we look on the reactants, on the reactant side, and we see hydrogen here, we already talked about as +1. That's its rule when it's involved in an all non-metal compound. On the product side, it is now hydrogen gas in its diatomic form or free state form. This is in its free state now as a diatomic. So its oxidation number is 0. So this hydrogen has gone from +1 to 0, meaning it gained 1 electron. So electrons are now officially being gained and lost. It is lost by the magnesium and gained by the hydrogen. The next lecture, we'll talk about redox and what all this means and how to balance with redox reactions.